Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is plate and shell modeling in RFEM Part 2. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in the way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, the purpose of this two-part webinar series was to give a complete introduction to RFEM for plate, shell, or surface modeling, analysis, and design. This is part 2 of the webinar series. So if you did miss part 1, you can find a recording of that on our YouTube channel as well as our website. And in part 1, we really focused on modeling the structure from scratch, which would be this tank structure that we're seeing here. We also applied loads to the structure and set up our load combinations per the ASCE 7, but we did not run any of the analysis or calculation portion, which is what we'll be doing today. So we'll be taking a look at a detailed review of these analysis results. Then I want to get into one of our add-on modules within the main program RFEM called RF Steel Surfaces. This will allow us to design a general steel surface based on stresses only. I want to also address surface singularities and how we can combat these within an FEA program. We'll also get into our other add-on module, RF Stability, where we'll be looking at plate buckling behavior, and we'll also be relating this to modeling imperfections with our additional add-on module, RF-IMP. So we can get into our example today, and I will jump over to RFEM. As we saw from the first webinar, this is the tank structure that we previously modeled. And we also had applied the loads to the structure, and we can see that within our drop-down box here are our different load cases. We have self-weight, which I don't have any visible loads displayed here because I didn't apply anything to the dead load other than accounting for the self-weight. The load case 2 here is the fill load, and this fill load was just an interior surface load within the inside of the tank. We also have a wind load, so we can see the windward direction here from the global x-axis. We have a suction force on the leeward side. We also have a compression force coming up from underneath the tank, and we have a tension force up at the top here. Now we also put together all of our load combinations per the ASCE 7. So as we scroll through these, we can see all 3 of those different load cases acting together on the structure. So starting where we ended from webinar 1, we'd want to run a calculation, and we can go to calculate all. And for the sake of time, I've already went ahead and done so. So what we would be presented once we run the calculation is our results. And within the project navigator, we should now have this 4th tab available to us called results. And I think it's helpful if we just collapse most of these trees here, just to slowly go through all of the visible options, and we'll start off with the global deformations. So as I'm scrolling through these different load cases and load combinations, and I can go ahead and turn off my loads as well, I'll see the general deflection of the structure. So this might be helpful in understanding the behavior under the applied loads. If we see something kind of flying off the page here, then we would understand that maybe we didn't correctly model something, or maybe our loads were incorrectly applied. So it just gives us a sense here if everything is going well. What else might be important is I'm going to jump back here to my fill load. And you remember that from webinar 1, when I double click on this fill load, we actually have it increasing linear in the Z direction. And what I mean by this is at the top of the tank, I want this fill load to be 0. But as we slowly increase the depth here, we eventually reach a magnitude of 0.4 kips per square foot, which makes sense. The bottom of the tank is going to see a higher fill load than the top. So what I can do with this particular load case after I have run my results is to turn off the global deformations, and instead I can take a look at the distribution of load. So when I view the distribution of load in the local Z direction, we actually can see how this load was distributed on the FE elements. At the top, we have this blue color, and that indicates we have 0 kips per square foot, which is exactly what I defined with that particular surface load. But as we take a look at the bottom of the structure, we have these red contours defined, which equals 0.4 kips per square foot. So just a nice validation here that we correctly applied that fill load. In a similar sense, we can take a look at the wind load. So remember, if I display this load again here, we have this wind load acting in the global X direction. Well, looking at the distribution of the load with these contours, I should see my highest compression force here on this windward side, which relates to the negative value here. And then in the back, we have this suction or tension force, which is denoted by this yellow positive value at about 0.01 kips per square foot. Now, at the sides, I should see essentially 0 because the wind's passing right over each of the side surfaces. And of course, that's denoted by the green color. If we take a look at the bottom, this shows the correct compression forces here. And then at the top, we have these suction forces denoted by the red with a positive 0.026. So again, just a nice validation to ensure that we've applied our loads in the correct manner. We also can take a look at the entire structure by selecting it here with my selection box. I can right click and I have the ability here to view the center of gravity and info. Now the program throws up a warning that says some elements have 0 density. They're not going to be included with the center of gravity. We know this because in webinar 1 we created all of these different intersections with our surfaces and we deactivated components. We also have our rigid component here for the top of our manhole that we would not want to consider necessarily for the density. So that's why those are set at 0. But what this will give us is the information of the center of gravity, and we can also create a new node here. Now I know it's difficult for you guys to see, but there is a red arrow back here pointing to the center of gravity. But more importantly, we can get information such as the surface area, the coating of the surfaces. So why would the coating be important? Well, if we wanted to layer some type of coating on this tank structure or paint, we actually have the area in inches squared here of how much paint might be required. We have the volume of the material as well as the weight of the material. So just a general summary of all of our surfaces that we have modeled. In a similar sense, I can take a look at my tables, and I will jump to my results here, which is table 4. I can view my results summary. And what might be interesting is to jump down to load case 2, our fill load again. Well, we can view the sum of the loads in the Z direction, and you can see it's set at negative 3.03 kips. So this is the total load from that interior fill load that I've applied. Well, we would expect then for our support reactions to match this sum of loads. So when I activate the support reactions here in my project navigator, we can turn on the global, and I want to make sure I'm under the fill load here. We can turn on the global Z components, and you'll notice that sure enough, we have 3 reactions in the vertical Z direction at 1.01. So these add up to the sum of loads for LC2, the fill load, at negative 3.03. So again, just kind of checking here that everything matches up quite well. Now we can really move on to the results of our surfaces. So with this, I can expand my tree here for my surfaces, and maybe we jump to one of these different load combinations here to view our results. Now, what we have visible to us here is local deformations. So these are based on the lowercase x, y, and z axes. So this is related to the individual axes here of each surface rather than our global axes. But we can also view the basic internal forces. And what I'll do here is maybe just activate a single surface and change the visibility by the selected objects. And I'll zoom in here. And let me also right click to turn on the local axes of this surface element. So we're currently viewing the bending MX. We also have MY. We can view the shear forces as well as the axial forces, NX, NY, and XY. One thing to note here that is unique for surfaces is that MX is not bending about the local axes, it's along the local axes. So this is contrary to our belief for 1D members that MX would be bending about the local x-axis. So surfaces or plate elements have a different convention here. One thing that I think is helpful to understand how these internal forces are calculated or the convention related to these local axes is under the help manual. We can take a look at the manual in PDF format for RFEM, or we can also access the online manual on our website. So if you go to dlubal.com, you'll also find under downloads and info online manuals. And I'm currently looking at the RFEM online manual, chapter 8 for results. And if we scroll down here to section 815 for basic internal forces, the reason why I wanted to point this out is because it shows a nice picture here of the internal forces in relationship to the local X, Y, and Z axes. So again, we can see something like MX is bending along the X axes, MY is bending along the Y axes. We also see these axial forces, shear forces all shown here. So this just gives us a little bit better view of how exactly those forces relate to the local axes. Now keep in mind too that for all of these internal forces, this is true for stresses as well. The equations are directly within the help manual. So if we're curious to know exactly how these internal forces are calculated, again, refer to the manual. So going back to RFEM then, that will essentially sum up the internal forces. But you'll notice that the next option, if I expand the tree here, is principal internal forces. And this is showing me M1, M2, we have N1 and N2. So what exactly is the difference here between the basic internal forces versus the principal internal forces? And the basic is really internal forces to the freely defined X, Y, and Z local axes, as we already discussed. Well, for the principal, we will represent the extreme values of the internal forces. Essentially, we'll take the basic internal forces that we just saw and transform them in the principal axis direction. So principal axis 1 will be the maximum value. So we can see here M1. Then we have the axis 2, which is the minimum value. And we also can display this alpha factor here. And the alpha is going to be the angle between the local x or the y axes and the principal axes 1 or 2. And we need to increase the trajectory factor here. So I do so quite a bit. And then we can see down at the bottom, those trajectories are visible to us. So again, that's going to give us the angle between our local x-axis and our principal axes. Now, in some scenarios with a completely straight surface, flat surface, maybe there is no difference between basic internal forces and principal. Looking at the design internal forces, this is really more relevant to concrete design. So we're going to give you the positive and negative bending internal forces for the top of the surface versus the bottom of the surface. So you can imagine how that's beneficial for concrete design. This might be used if we weren't utilizing the add-on module within RFEM, but rather we wanted to take these internal forces into our own in-house tools or spreadsheets to do design. Now, today we have steel surfaces, so this really isn't of much interest to us. Now we have the stresses also listed to us here. As far as the stresses, these are only available within RFEM when you have purchased RF Steel, the add-on module. And RF Steel, which we'll actually get into in just a minute, but it also releases these stresses within the main program. So if you did not purchase that add-on module, you would not see the stresses available here. Now, this is true for all materials, even timber stresses, for example. You would need to purchase the RF Steel add-on module, which I know sounds a little bit counterintuitive, but essentially that's releasing these stresses here that we are currently viewing. So we can view the normal stresses in the X and Y direction, shear stresses, but we also have the principal normal stresses and principal shear stresses as well, based on those principal axes we just discussed. A little bit further down, you can see our equivalent stresses, and these are based on 4 different hypotheses. So you can see here we have von Mises, Tresca, Rankine, and the Bach theory. Quite common would probably be to refer to the von Mises for design. We also can close down these stresses and view the strains in a similar manner. So we have our strains based on the local XY axes, principal strains, and then of course equivalent strains as well, which again are based on those 4 different hypotheses shown here, which maybe von Mises is most relevant to our design. Jumping back to one of the basic internal forces here, it doesn't really matter which one. I'm going to cancel out this visibility. I thought it would be a nice feature here, and if I turn off my local axes of the entire structure, what we can do to view the interior stresses of this kind of enclosed tank is to take advantage of our clipping plane. So under Insert, we have clipping plane. What this will do is essentially kind of slice through our tank here so that we can see the interior stresses. And we can set a step distance of 1 inch, for example, and then we can use our offset button here to click around within our structure, which will essentially just kind of cut through that structure with this clipping plane. We also can change the planes that we're viewing, this clipping plane, and even more so, we can change the rotation. So we can change this to 25 degrees, for example. So now we're kind of viewing this clipping at an angle. So obviously the clipping plane may be an advantage to use when we're looking at these enclosed type structures such as tank elements. Where it's an even bigger advantage, as you can imagine, would be with 3D solid elements. So where we truly can't visualize the stresses on the interior of the solid element, well, clipping planes can become very useful. So currently, we're looking at everything graphically, but I wanted to also point out that all of this information that we're seeing visually here is also available in table format. And we can view again under table 4.0 the results. Perhaps we jump to the surfaces for the basic internal forces. Now there's a couple things I want to point out here is that we're currently viewing each surface, and you can see the program kind of syncs up in the background which surface we're looking at. But if we jump down here to surface number 5, you'll notice that only a single point is given to me here with internal force values. So why is that? Well, I'm going to create this visibility by the selected objects to take a look at surface number 5 here. And you'll see that single point given to me right here in the center. This is a problem. Obviously, we're much more interested in the internal forces going on around this entire surface. So why is there only one value given? Well, that's because you'll notice the results are based on grid points. If I double click this surface to edit it, we have a tab here called Grid. And by default, the grid spacing is set at every 1 foot. Well, this is entirely too big for our model today. Now, this tank structure is fairly small, so we need to go back, and in webinar 1, we did this with the FE elements. We want to do the same with these grid spacings to change this to maybe something like 0.5 inch spacing. And I click OK. So now you'll notice with surface number 5, I have many more points available to me here. So this is obviously going to be much more beneficial than just a single point element. Now the question might be, well, is the analysis incorrect without changing those grid points? And the answer is no. The analysis stays the same. You'll notice that we didn't have to rerun it. Everything that we're viewing visually here is based on the FE mesh element points. And if I turn off my results here, turn off my loads, these FE mesh points are producing the results, and then we can graphically see this with the nice contours. But when it comes to the table, we're not presenting the results based on every FE mesh point. You can see that it's kind of all over the place. There's really no nice pattern to the FE mesh. So that's why we're presenting it to you in grid points, so that every 0.5 inch spacing we're getting a result, which makes a little bit more sense than maybe necessarily displaying every FE mesh point. So what we would need to do here is to cancel our visibility mode, and let's kind of zoom out to the entire structure. We would want to select all surfaces. We can double click on them. Under the grid tab, we can change the grid spacing of all surfaces at once to 0.5 inches, and we click OK. And so now we're going to see much better results within our table. Now, keep in mind for these table results, we can export this single table automatically to Microsoft Excel. So I can just simply click this button here. The program will take this current table I'm looking at it, export it over to a Microsoft Excel spreadsheet. If we wanted to export multiple tables at once, and maybe for multiple load combinations or load cases, well, that's possible by going to File, Export. And here we have an XLS format. When I click OK to export to Microsoft Excel, this gives me quite a few more options. You'll notice here I can activate my results, for example. And I can take a look at these detail settings here for the selected tables. I can turn on several load combinations or all of them. I also can select different tables to export. So you can imagine this is quite a bit more efficient in terms of exporting rather than every single table from what I previously showed you. But if you are just looking for a quick export to further sort or filter data, then of course this is possible here. Okay, so that really just gives an overall summary of the analysis results within RFEM. What I would like to cover now is the general stress design of these surfaces utilizing our add-on module RF Steel. So I already mentioned that RF Steel releases the stresses within the RFEM analysis, but it also can be used to do a general stress design. So we can access the add-on modules, as I pointed out in Webinar 1, under our Project Navigator. Here's our long list of add-on modules. RF Steel Surfaces is at the top because I've right-clicked. I've activated it as one of my favorites to kind of jump it up to the top here. We also can access all the add-on modules from our drop-down box up at the top under Design for Steel, and you'll see here RF Steel Surfaces. So with this add-on module, as I always like to mention, it's just a simple dialog box that pops up within the main program RFEM. I don't need to remodel the structure. I don't need to redefine loads. Even all of those internal forces and stresses have already been solved for. So all of that information is coming into this add-on module. We're just specifying a little bit more information specific to the general stress design. Now keep in mind also that this is completely code independent. So we're not designing per any particular code. We're just comparing the stresses from the analysis to the limiting stresses based on the material. By default, the program selects all surfaces to be designed, and I don't want that today, but rather I'm going to graphically select which surfaces. So under the Display tab, under the Views tab, is where I'm going to activate my surfaces by thickness. So I'm going to choose here my surfaces that are 0.2 inches thick as well as 0.12 inches thick. So this will highlight only in the graphical view here the body of the tank as well as the legs. So these are the only surfaces I'm interested in designing at the moment. You'll notice everything else is hidden, including the components on our roof. When I click OK, all of those surfaces are individually listed out here. For the ultimate limit state, I want to move my LRFD load combinations over to the right-hand side here to be considered for design. Now, additionally, I could select the result combination to be moved over to the right-hand side, or I could just design the result combination itself. If we remember from webinar 1, result combinations are going to be an envelope solution. So I have RC1 here, which would be the envelope solution for all my LRFD load combinations, showing me the max and mins. I prefer to list out the load combinations individually because then I can see my max and mins from each individual load combination, but either are possible. The serviceability limit state is to check deflections. So for my tank example today, I'm really not so concerned with checking my deflections, but if we were designing some type of, I don't know, floor element or maybe an industrial structure that's very sensitive to some machinery that we're putting on it where deflections truly is a concern, then this is where we would want to move our ASD load combinations over to the right-hand side to be considered for serviceability. So we'll just leave those blank for now, and we'll move back to the ultimate limit state, and we'll continue down our list here. The materials are automatically brought in from RFEM. So we have our stainless steel material, and the yield strength is given to me as 30 KSI, and then the limiting stresses are automatically filled out here. So we can see the limiting normal stresses as well as shear stresses. So these are the values that the program is going to compare to my analysis stresses to give me an overall design ratio. Now you can also choose to manually override these. So the program automatically sets them based on the yield strength, but you can go ahead and click this manually button to override those. We won't be doing that today. What else we can do is under these edit material settings is to set a few different ranges here based on the material thickness. So perhaps for a thicker surface, we might have a higher yield strength. So we can set those ranges for the thickness here, as well as the equivalent yield strength, and then the program will consider that for the design of our surface. Now today, that's not so important because we have only uniform thicknesses here for our surface elements, but that is one option to consider. Now, also within RF steel, this isn't specific to only steel materials. For example, if you wanted to do a general stress design for aluminum, you could bring an aluminum material in here. You would need to modify the limiting stresses manually, but then we could also do a general stress design for aluminum surfaces as well. So it is not only limited to just steel. Under the third table here, surfaces, these are all my individual surfaces listed out that I'm designing, as well as the thickness. We can optimize within the add-on module. So when I choose this checkbox, the program brings up a dialog box that asks me the range for the surface thickness I'd like to optimize within. So I give it a min and max range, as well as the increment to increase or decrease. Then I set the max available stress ratio. The default is 1.0, but we would probably think for design purposes, maybe we set this at 0.8. The program will automatically optimize these surface thicknesses based on the range we've given it, trying to get as close to 0.8 or whatever ratio you've set possible. So maybe we can come up with a little bit more of an economic design by having the program modify those thicknesses for us. We won't be optimizing today though. So when I run the calculation, we'll actually see that it solves pretty quick because we already have all of our stresses from RFEM and the analysis for LRFD load combinations. We're just bringing them into this add-on module and we're comparing to the limiting stresses based on the material. So we now have our results tables available to us, and we can view the stresses by load case, these stresses by material, or these stresses by surface. When I pull this down, we can see that everything again is synced up in the background. We have the red arrow pointing to where the controlling internal force is, as well as the surface is highlighted that we're currently looking at. So here's the column for existing stresses, all listed out. Here's my limiting stresses based purely on the material. And from this information, we get the general stress design ratio. Now there are only a handful of stresses listed out here. Under the Details tab, this is where you can control what stresses are turned on or off and used for this design. By default, we have already selected a handful of stresses available. We don't want to check all of them. That's completely overwhelming and may not be necessary for the design. But if you're interested in turning on or off some different stresses here, you can do so under this Details tab. So for the most part, most of these stress design ratios look okay. But when I take a look at the filter options here to kind of filter to the max design ratios, and we view the summary down at the bottom here, I have a max check of 1.4, which is greater than 1.0. So I'm shown here my red sad face. This is obviously something that we need to address. We're over that yield strength. So how can we do so? Well, let's take a look at graphically what's going on rather than just in our tables. So I'm going to click here to my equivalent von Mises stresses. You'll notice it's for load combination 3, and I can click on my graphics. Well, most of the tank here, when we look at our von Mises stresses, and keep in mind that we're still within this add-on module RF steel, we just can view the stresses or the stress design ratios graphically. When I scroll in here, we just have these teeny tiny points that are really causing the issue, and everything else looks completely fine. So this is what we would call a singularity. Singularity is not unique to RFEM. It can happen in any finite element analysis software. And it's really a point, an FE mesh point, where we just have a very high stress concentration and we're not getting great load distribution. And we know in reality where this tank body is connecting to the tank legs here that we're going to get much better load distribution all along this length than what the program is showing me. So how can we better tell the program that the load distribution is there, that these high stress or high peak points that are causing the over design of my general stresses to be much too high? Well, let me jump to load combination 3 here, because we have determined that that's the controlling load combination, and I'm going to turn on my stresses, my von Mises stresses. So this is exactly what we were looking at within the add-on module itself. Under the display tab, and what I've done here under the display tab, this is typically what would be available. I know it looks a little bit overwhelming, but again, we can collapse these trees, and eventually I want to focus on this results portion here. We also have these surfaces, which I can expand under the results, and the distribution of internal forces and stresses. And you'll notice here that we have several options for how we display these stresses. The third option is default here, but I want to focus on the 4 options, the first 4 options, and what exactly they mean within the program. And for this, I'll jump to the PowerPoint. So as far as the display of surface results and those 4 options, number 3 here is default within the program, and we'll get to that in just a minute. But let me begin by explaining that the concept here of these 4 pictures is that we have 2 adjacent surfaces. The surface on the left is denoted by 6 FE mesh elements with their individual boxes here, and then we have a surface element adjacent to it indicated by these 3 FE mesh elements. So when we choose the first option, constant on elements, well, we have every FE mesh element point here, right? And we're going to average out those 4 points for a single FE mesh element, and we're going to give you that average value right here in the center. Then we're going to base our colored contours only on that average value. So each FE mesh element will only have one color here. The second option, non-continuous, you can see that there are quite a bit more results available because instead of averaging out those 4 corner values, what we're going to do is display them separately for each FE element. So now you'll see you'll have multiple color contours within a single FE mesh element. The third option is continuous within surfaces, and this is the default within the program. So what we do here is we'll take the average at the FE mesh point itself, then we'll use a smoothing algorithm to tie these values together in nice contours so that it creates a great display when we're viewing it within RFEM. But notice we do have a clear hard line here between surfaces. So my surface on the left has its own contours and my surface on the right has separate contours. And quite honestly, this is default because this works quite well in a majority of cases, especially when we're looking at a more global scale of maybe a concrete slab element. Now, the fourth option here, continuous total, well, what this is going to do is going to use that smoothing algorithm to tie adjacent surfaces together here. So now you won't see this hard line between two surfaces, but rather the nice contour will fill between the two adjacent surfaces. So again, number 3 is typically fine, that's why it's default, but there are scenarios, especially when we're looking at a much more local scale here of where these small little elements are connecting in every FE mesh point, that we want to change this to actually constant on elements. So going back to the RFEM model then, you'll notice here that when I have this as a default, continuous within surfaces, my von Mises stresses is set at 37 KSI. When I change this to constant on elements, now notice that each FE element has its own color, the stress drops significantly from 37 KSI clear down to 16 KSI. That's a huge difference. Now, again, this doesn't relate to what's right versus what's wrong with the analysis itself. It's just purely how we're viewing our results graphically here. And just by changing this view, you can see how much those stresses are impacted. Now, when I go back to the add-on module RF Steel, let's go ahead and launch this add-on module. And I want to point out that I changed my display, as we saw back in RFEM. But when I'm looking at the total stress design ratios here, they're still showing 1.4, which we know our highest equivalent von Mises stresses, for example, is only 16, so we should be well below this. Well, the reason why is under details, we need to set this under the options as well. We would change the distribution of internal forces to constant on elements. So although we've changed it back in RFEM, the add-on module has its own separate option here that we would want to change that. So when I click OK, the program says, okay, I need to recalculate the results then. So we go ahead and let it bring in those internal forces again. It compares to the limiting design stresses. And sure enough, you can see my max design ratio is now 0.62. So just by changing the view of our results, we can really significantly impact the overstress design ratios within the add-on module. Now, with that said, if we take a look here, stresses by surface, I don't know, we take a look at the von Mises stresses, for example, and I jump to my graphics view again. So I'd still like to point out, though, we took care of this high design stress ratio. We're definitely sitting much better, but I'd still argue that there's a singularity still occurring at this location. Again, I mean, if you look at the rest of the structure, the stresses are so low, but when we look at these FE mesh points, they're still relatively high. So I want to take this a step further to address these singularities by applying what's called an average region. So under the Data tab, what I can do is to access a new average region by right-clicking on it. We launch the dialog box, new average region, and it's exactly as it sounds. What we're going to do is to average out the internal forces over a particular region. And this is quite powerful because I can select multiple surfaces here to be considered. So we'll select the tank body. Maybe I also select these two surfaces from my tank leg. And I click OK. So we need to define the average region as a circle as well as the dimensions. And the dimensions, I will set this at 2 inches. Now, the question that we may get is, well, how big to set the average region? And this really depends on your project, and it's up to the engineer's discretion. We're working with a very small tank here, so 2 inches is adequate just to apply this smoothing region at this particular location. But you can imagine if we set this at something like 2 feet, that's entirely too big to average out the internal forces. But 2 feet might be perfectly fine when we're averaging out a concrete slab where we have a column framing in. So again, it really just depends on your project. We want to tell the program where to place this average region. So graphically, I can select this node here. The coordinates are automatically populated. I'm going to choose all 4 checkboxes here. What this does is it averages out the internal forces in all directions. This is based on the local axes, U and V, of the average region versus the local axes of the surface, X and Y. We need to specify a projection direction, and we have the global X, Y, and Z axes given to us here, but from RFEM Webinar 1, we remember that working with this circular tank structure, we're not so much able to relate the model to these global axes so easily. So instead, what I can do is to choose my own direction vector to kind of average out these forces. So when I choose this option, what this allows me to do is to graphically select a couple points. So I'll zoom out here, and I'll actually turn off my results, and I'm going to cancel my visibility mode. We remember from the first webinar, we created all of these points, and zooming into the bottom of my leg, I'm going to choose the center point here. My second point is going to be the center of the tank structure as a whole. So now this projection direction was automatically calculated, and you can see the parameter set here. We want to distribute the internal forces through all surfaces. So when I click OK, it might be better to turn this to a wireframe view. We have an average region defined here. And I know it's a little bit difficult to see, but you can see that we've applied this 2-inch little average region. It's being projected towards the center of the tank structure. So when I apply this average region, I'm going to view my results for load combination 3, and we can turn these on. And I'm going to kind of maneuver my model here and zoom into this point. I'm currently viewing my von Mises stresses, and notice that we no longer have these high peak forces here. So we're instead averaging out over this 2-inch diameter region for those von Mises stresses. Now, when you do apply average regions, you have a new checkbox here in your results where you can turn on and off the average region. So if I turn it off, well, here we go. There's those high stresses visible to us. We can activate the average region again, and they completely disappear. So we'd want to continue adding in these average regions to other locations here where the legs are framing into the tank body, just to kind of alleviate those high peaks. For the sake of time, we won't be doing that today, but hopefully you have some insight on how to apply average regions for kind of odd structures like this. Obviously, a flat surface would be much easier to apply an average region in terms of the projection direction and such. Now back under the Data tab and RF steel surfaces, in a very similar manner that we saw previously with the display of internal forces, under the Details tab and under the Options tab, we do need to apply the smoothed internal forces from the defined average regions. Otherwise, they will not be considered. So we just take that extra step within the add-on module to, yes, please consider them with the design. The program will cycle through the quick analysis again, and we will be presented with our results. Now, I didn't apply the average regions to the other locations, so we're still seeing the same design ratio, but we would expect this to fall significantly, and then maybe we could optimize our tank thickness quite a bit further. All right, so that really explains a general stress design for these surface elements utilizing that add-on module. The next thing that we would like to discuss is the stability design, and in particular, the buckling behavior of this structure, and we'll be relating that to imperfections. So I'm going to launch RF stability from my list of add-on modules here. And when I do so, the add-on module has a similar feel to what we saw with RF steel surfaces. Now it's a little bit different. This is going to allow us to run an eigenvalue analysis on the structure. In previous webinars, I've used RF stability to track down instabilities. We all know that instabilities can be incredibly frustrating within a finite element software, so RF stability can be extremely helpful in tracking down where exactly we may have a problem. But today I'm going to be utilizing the add-on module to do a general buckling analysis to identify kind of modes of failure for the structure under the applied loads. The number of eigenvalues needs to be defined, and the default is 4, so we'll just leave that as we have defined here. We want to import in either a load case or a load combination. So my kind of worst case scenario has been load combination 3, and you certainly want to import in either a load case or combination that has the highest axial forces. We know that this is going to give the worst buckling failure modes as opposed to importing in something that's, applying tension forces. For example, the program will throw up a warning that says, hey, I can't really apply the eigenvalue analysis for buckling because we have tension forces. So something to keep in mind there. Now, the stability analysis calculation method by default is set to an eigenvalue analysis. This is a linear analysis. And this is what we'll first be running through today, just for a quick calculation. Keep in mind that nonlinearities within the RFEM model will not be considered. We do have the second option here to run a nonlinear analysis. And this actually will consider any geometric or material nonlinearities back within the main model. And we have the ability to incrementally increase the load. And this whole section I'm going to get into a little bit later on at the end of the webinar today, because I think it's actually pretty powerful in what we can do with a nonlinear buckling analysis. But for my initial calculation here, I just want to run a linear analysis, get the basic buckling failure modes. Now, when I click calculate, what the program's doing is running through these first 4 eigenvalues. You can run up to 100 eigenvalues if you want, but it really doesn't make much sense when we're looking at those higher eigenvalues because the buckling mode failure will probably never occur. It's taking extremely high loads to even see that type of buckling mode. So that's why we set this at 4 eigenvalues, and this will just kind of give us the general failure modes within our structure today. So once this is done solving, we will be presented our results here within table format, and we see here the first 4 eigenvalues given to us, and we also can scroll through these, and you'll notice in the background the RFEM model is synced to what mode shape we're currently viewing, and it looks to be, essentially buckling of this leg over on the right-hand side for the first 4 eigenvalues. And we're also presented with the critical load factors. So these critical load factors is the value that you can multiply load combination 3 here that we imported by before we're going to see the failure buckling mode that's shown in the background here. So that's why you can imagine that additional eigenvalues may not be so relevant when we're getting into some of those higher numbers. But of course, if we were solving for higher numbers, we might see buckling of the other 2 legs. We might even see buckling of the tank body itself. So something to play around with. Looking at the first eigenmode shape, we can jump to our graphics view. Now, once again, we are currently in the RF stability add-on module. I'm just viewing my results graphically here, and under this second option within my panel, we also can drop to the different eigenmode buckling failure modes here if we'd like. So everything has to do again with this leg over on the right hand side. So the eigenmode is shown to us here, and I can actually right click on the boundary line element of my leg surface here. When I right click on it, I can choose results diagram. What this will bring up is the buckling mode shape here in kind of a results diagram format. And actually, let me turn on the Y direction here so we can see the buckling behavior of that leg element along that line. Now, the reason that I'm doing this whole procedure is because I want to relate this buckling to modeling imperfections. And we all know that when we are constructing a tank or any type of structure, that there are installation errors, maybe there's incorrect construction methods, or we don't properly manufacture the elements, and inevitably we have imperfections. And everything that we are modeling within the RFEM program here is perfect, essentially. And this is true for any general finite element analysis. All lines are perfectly straight. All elements join together at every FE mesh point, when we know that in reality, lines probably won't be straight. Surfaces aren't in all one plane. You know, mistakes happen, and there are tolerances that are given, though, for these mistakes. And this comes from the AISC Code of Standard Practice, and in particular, Section 713.1. It discusses misalignment of members and surfaces and such. And these tolerances can be less than L over 500, where L is the distance between working points. So keep in mind that L is not the distance between the start of my surface and the end of my surface, but rather I want to use my working points here where I see my inflection points. So looking at the general buckling view here, I take a look at the first inflection point taking place at about 10 inches, and then I scroll over here to the end at 17 inches. Well, this would be my working point at about 7 inches in total. So what we want to do here then is to model the imperfection, keeping this into consideration with these tolerances. And I also want to backtrack and just mention something like the AISC 360 tells us that we should really model these imperfections directly. There are other alternative methods such as applying notional loads and such, but in some way or another they should be accounted for. So we're going to refer to the AISC Code of Standard Practice. So now that I have my working distance here, we'll notice that because RF stability just runs a general eigenvalue analysis, nothing is given to us here in terms of a length. Everything is unitless. So this buckling mode ranges from 0 to 1.0. So what I like to do is to model this imperfection that can potentially occur and scale it based on L over 500. With my L being 7 inches divided by 500, we would want to scale this to 0.014 inches. That's just 7 divided by 100. This is where I'm going to activate my other add-on module called RF-IMP. And RF-IMP is pretty powerful because what this allows me to do is to import in a buckling mode from RF stability. So we'll choose our first buckling mode. And I'm going to scale this because remember, once again, RF stability is unitless. So we're scaling to 0.014 inches given to us by the AISC Code of Standard Practice. And we can actually generate the pre-deformed FE mesh in order to affect the imperfections of the surfaces. So when I click calculate here, what the program is doing is it's actually going to deform the FE mesh based on the scaled buckling mode. Then we'll be able to consider that before we even run the additional load cases such as dead, live, or wind load. So after RF RF-IMP is done with the calculation. I can see here every single FE mesh point listed from my model, and most are set at 0, 0, 0 because nothing's really unchanged. But we eventually get to a point down here where we have some of these values that are being modified. So you can see the big red arrow. The program's telling me, okay, I'm going to deform the FE mesh at this location based on the scale of 0.014 inches that you gave me. So now this can be considered as an imperfection and we can directly model it. So once I'm done with the deformed mesh, I need to go up here to my load cases and combinations. And we visited this topic, this dialog box in quite a bit of detail within the first webinar. Under the Load Combinations tab, remember we generated all of our load combinations automatically according to the ASCE 7. So I'm going to create my own manual load combination here, which I can select it from this button down here in the lower left-hand corner, and I'm going to replicate load combination 3. So I'm going to call it 1.2 dead plus live plus wind. So identical to load combination 3 that we're seeing up here, but I'm going to take this a step further to apply my imperfection that I just created with that kind of deformed FE mesh. So I move all of my load cases over to the right hand side to be considered, and I'll change my load factor here for dead load to 1.2. Under the calculation parameters, we have the extra options button. The extra options allows me to activate my deformed mesh from RF-IMP. So that imperfection, the deformed mesh, is now considered with these load cases I've defined here. I click OK. And we can run this load combination by starting our results. Now I am running according to a second order analysis just to give us some quick results here. Maybe in reality we would want to run according to a third order analysis just to get even further into the analysis and the details. So I went ahead and ran this. I'm reviewing our stresses on the structure just like what we've seen before. And in reality, I'm looking at my von Mises stresses. There really isn't much difference here with my leg on the right hand side. But I also didn't really scale that imperfection up too high, only 0.014. So I think it can be concluded that it really doesn't have much impact then maybe on the stresses at this location, which isn't necessarily a bad thing. Maybe if we had a thinner material here for our leg elements, we would see more of the results. But in order to make sure that the deformed mesh was applied, I did notice when I turned on my global deformations in the Y direction that we can see that this buckling kind of mode shape with the deformed mesh is considered. We have ever so slightly some deflection here in the Y direction that indicates that that mesh was deformed. So possibly with a third order analysis too, we could even see more of those results available to us. But this in general is just one way that we can directly model these imperfections, because again, not everything is going to be perfect as we're modeling here, but rather there will be errors with the manufacturing or installation process. So the final thing that I'd like to show you today relates back, if you were mentioned, to RF stability. I said that we would touch on a nonlinear analysis for the buckling behavior of the structure. And instead of going back to the add-on module, what I'm going to do is to access my load cases and combinations again. And I'd like to point out that under the calculation parameters, if you remember, I briefly showed this to you in RF stability for the nonlinear analysis. We actually have all those same options directly within the RFEM program itself under the particular load combination. So we can incrementally increase a load here until our structure fails. So you do need a license of RF stability in order to access this information. The reason why I'm doing it here in the load combination itself is because we have a couple other options that are not available to us within RF stability. So slightly more powerful here. So what I'd like to do is to once again create a new load combination. And we will call this one 1.2 dead plus live plus wind plus our imperfection. And taking it one step further, we will check out this structure until it completely fails with this buckling method. So load combination 3 here is still considering the imperfection, plus we're going to activate the incrementally increased loading. So what exactly can we do here? Well, we're going to set the initial load factor to 100%. That just means that my loads from load combination 3 will be 100% applied to the structure. Then I'm going to increase the loads by 1.0 for every subsequent increment after that. So I'm going to apply 100% of my loads, 200%, 300%, 400%, on and on until the structure fails. I'm going to refine the last load increment by 10. This just means that when the program decides, okay, I can no longer take any more load, let me refine this within the last load increment so I can just get a little bit more of a detailed factor of how much load I can actually apply before failure occurs. We also can select a stopping condition. So if my deflections exceed 6 inches, then the calculation will stop. I think we can all agree that if this tank is deflecting more than 6 inches, then it's probably close to failure mode. Now, this option here is very unique and also powerful, because what I'd like to do is to not consider my self-weight necessarily being multiplied by this load factor. And what I mean by this is I'll create a new load combination quickly here, and we'll call this one 1.2 dead. And I'm going to move my self-weight over, and I'm going to change my load factor to 1.2. My second tab here, I'm not changing anything. Everything is default. I'm not activating any of these extra options. Back under my previous load combination 12, I can actually import in this self-weight load combination only. So it will not be considered when I'm incrementally increasing the loading. Only my live load and my win load will be increased. And that probably makes the most sense. We're not going to sit here and multiply our self-weight by additional factors to see how our structure will fail, because that really will never happen. So that allows us to do so. Now remember, we also want to activate the extra options here and to import in our deformed mesh from RF-IMP. We also have the ability to save the results of all load increments. So this is really powerful. Once we get to the results, we can visually see as the structure begins to fail. I do want to change this to large deformation analysis. And finally, under the General tab, I need to move both the fill and the win load over to the right-hand side. Now notice I did not move the self-weight because we've already accounted for it under the second tab here to use the initial loading so that it's not increased. So once we have defined this load combination completely, I can click OK. And the program asks me to clear the results. That's fine. And we would want to run the calculation by clicking on this show results for this single load combination. For the sake of time, I went ahead and did so just because it does take a minute to solve. And we will be presented here with our deformation, our results for this particular load combination. And what we have the ability here is to view the different increments. Remember, that was one of the checkboxes I just selected. So maybe I change my deformation factor to 30, so it's not quite so big. We can lock that down here so that it doesn't change as I change my increments. The other thing I'd like to do is under the Display tab, I'm going to hide my results, and we're going to look at this FE mesh settings. Now it's default here to show the FE mesh on the surfaces, but I'm going to change that to the surface results. So as my structure begins to deflect here, the FE mesh will also follow. It just makes the view a little bit easier to see what's exactly going on. So here's my first load increment. 100% of my loads from load combination 3 are applied. But now I can begin to scroll through these different load increments to see the structure deflect under 800%, 900%, 1,000% of the loads. And what will be most apparent here is if I take a look and I zoom in, we can actually see the buckling of that leg element. And I can even take my leg here and highlight it by choosing the visibility by the selected objects, so we can really see the source of failure for this particular leg, and we can continue on with the additional load increments. Now I can activate the rest of my structure here graphically. So as we're reaching these higher load increments, the structure is still holding on. We're seeing very, very large deformations here. I mean, of course, the deformation factor is set at 30, but obviously the leg is a problem until we get to a point that the program says, okay, I can't handle anymore. It's reached 29 load increments and the structure has completely failed. So we might be interested in the load increment 28 here, and we can even scale down our factor to 10 just to see moments right before the structure fails. Now, these load increments are pretty high, but you can imagine that when we're dealing with a much more sensitive structure, an existing structure, that we want to see how different applied loads on the structure can impact the failure mode, then this might be a very interesting approach within the program. Then we can determine how we would want to modify the structure. Okay, so that is essentially going to conclude our webinar today, and I will jump back to the PowerPoint for just a little bit of closing information. Please visit our website at dlubal.com to learn more about not only RFEM the program, but some of these add-on modules you've seen. Our web shop, we're also very transparent with our pricing information. I always encourage everyone to follow us on our social media accounts. YouTube, for example, has all of these previously recorded webinars that you can find. LinkedIn, Twitter is going to announce the events and conferences that we'll be at, new technical articles and FAQs, so it can be pretty beneficial if you are utilizing RFEM. If you have any questions about today's presentation or anything else, you can contact us in our Philadelphia office at info-us@dlubal.com, so feel free to send us an email there. Our phone number is 267-702-2815. We will have many more upcoming webinars. I try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. As most of you know, I send out a couple reminder emails about a week or so before these will take place, so you can register directly through the email as well. As far as PDH certificates, these will be issued automatically to all participants today. So if you did attend the webinar, you were here for the full 60 minutes, because this is required by the states which we are pre-approved to provide PDH certificates to, you will be receiving that PDH certificate within the next 24 hours. If there were any attendees that did not register themselves for this presentation, but maybe you watched with a colleague, for example, you would need to request PDH at the email address shown here, info-us@dlubal.com. So again, if you yourself did not register with your own email and your own name, and you are wanting PDH, please send us an email at the info-us email address. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at the next presentation. Thank you.